All right, let's get started. We're going to talk about Spark. We'll talk about what problem we are trying to solve. Let's get a quick understanding of why we want to. So one of the things I would like to do is, one of the most dangerous things we could do is be infatuated with technology. So if we start using technology without really understanding why we use it, then it becomes more problematic over time. So as I come across technologies, one of the things I try to understand is, what problem does it really solve? And once I understand the real problem it solves, then I can figure out if I do have that problem, particular problem, and then of course I can apply it. There are times when you may come across a technology, but it may be months, if not years before there might be a reason for using it. So my goal in this talk is to spend the time on understanding what the problem really is, first of all, and then take a look at how Spark can help solve that particular problem. So let's get started with a fairly simple example here. So one of the things we have done in the past about, I would say, 15 plus years is the growth of multi-core processors. There was a time when computers pretty much had one processor, and Moore's law said that computers will keep becoming faster and faster because we can package more and more. Well, Moore's law worked really well for quite a while. Down into the years 1980s and 1990s, we could just buy a machine every couple of years and it'll be faster. Well, then suddenly we found out we couldn't keep packing more into a particular chip, mainly because one of the consequences was the heat it was generating. And what fun is it to make the chip really run faster and have it melt in front of you on your lap? That's not going to be fun at all. So then they said, well, okay, we got to go to multi-cores. Well, you see, when you come to multi-core processors, in a single machine, a single processor, multi-threading is more multitasking. You got only one thread running at any given time, and it's context switching very heavily between those things. In a multi-core processor, multiple threads truly run exactly at the same time. So you get to really have true concurrency. But of course, the problem is when you have concurrency in your applications, a code that may pretend to work correctly on a single core may actually end up being broken on a multi-core processor. One of the reasons this could happen is because of contentions that may arise between multiple threads running at the same time. So we tend to deal with this. The solution for multi-threading has been in Java from day one. Had you been programming in C++ before that, there was no one solution in C++ to deal with concurrency. Depending on the platform, you had to use different solutions. But one of the really nice things Java did was, Java gave a very consistent API to do multi-threading from the day one. But unfortunately, even though they did, the first thing they did was they provided the thread class. And then it took us a few years to realize, as much as threads are lightweight, it's really not that lightweight. Because you don't want to be creating threads and killing threads and creating threads and killing threads. And then in Java 5 they said, oh dear, that's not really working well. Let's come up with a pool of threads, the executor services. Well, and then of course, around that, a lot of different APIs were created. But unfortunately, that still creates more problems for us. I'll go into that a little bit detail in a second. But let's just shift our focus to something else for a minute. When you take a problem, every problem we take has certain amount of complexity. You could say the problem is a simple problem, or the problem is a complex problem, right? So in this case, of course, if the problem is simple, you want to solve it, and if the problem is complex, you still need to solve it. But you want a simple problem to have a simple solution. You want a complex problem to have a manageable solution. Well, what if a simple problem ends up having a very complex solution? That would not be fun at all, because the problem is simple, but we can't solve it so easily, and we suffer the consequences of it. So let's take an example here, real quick, what would be a problem. So in here, I have a fairly trivial, simple problem. I have a function called sum of square roots. And all it's doing is, given a number, it computes the total of the square root of all the numbers. Nothing really earth-shaking, right? Then I have a, max is 50,000, and I have a sum of square roots, just to kind of tax the computation a little bit more. And I'm sequentially running through and finding the sum of the square roots and then totaling that to a bigger value. So if you look at this particular example, there's not a whole lot of complexity. It's a fairly simple problem after all. But what does it take to run this particular code? Let's just run this little piece of code. I'm just going to call the run.sh here to make my life a little easy. And you can see that it runs, takes a little while to run, and then comes back and gives us the result of 1.49 e power 11. How much time did it really take to run? Let's go ahead and time that one and see how much time it took. And you can see that in this case, it kind of runs through. And then eventually, after about 5 seconds of time, it told us the result. Yeah, okay, so it took us about 5 seconds. But I want to make it faster. So what am I going to do to make it faster? Well, clearly I could use executor services. So what am I going to do? I will create an executors service, for example, and then I could go ahead and initialize it. I won't do this here, but I'll bring in a code a few seconds later to use it. But then what am I going to do? Well, these has to get the work done and get you the result. So for this, what we could do is we could create a future. Oh, not just a future, a list of future, right? And there's more than one way to do this, but one way is to get a list of futures and you can initialize it. Then what do? Well, within this code, of course, what I could do is I could go in and say the list of futures, we'll call it futures.add. And then, of course, we'll take the executor service and say submit. And then we will give it a little task to execute, which will return an executor, which will return a future. Then we have to loop through over here to get the value from within the future itself. So we would have to do all that work ourselves. But when we are done with it, what's going to happen? Well, let's go ahead and take this code that we had a minute ago real quick. Let's keep this away, and then we'll come back and look at it. So I'm going to just take this one here, save it right here in this file for just a minute. And I'm going to then say, in this case, I'm going to bring in just a slightly different code, if you will. And this is the code that does this concurrently. So what am I doing now? Well, I didn't bother to change this part at this time. That's still doing what it did before. But notice I created the executor service like I promised a second ago. I created the list of futures like I said a minute ago. And then, of course, notice that we are looping through and getting the future added from the executor services submit. And then, of course, that's calling the sum of square root. Then we loop through yet another time, getting the futures and getting the value from the future and adding through it. And then eventually shut down the executor service, and then we await for termination. How many threads am I creating? That's a good question to ask. And I'm creating 1,000 threads. So I'm going to run this problem using 1,000 threads. Well, what's the good news? The code is no longer going to run sequentially. The code is going to run concurrently. And why are we doing this? To get a better performance, isn't it? So let's go ahead and run the code now. It is concurrent. It took us 5 seconds to run in the past, didn't it? So this time, it took us about 2 seconds to run. So we got some speed up in this. But don't trust it too much, because if I run it sequentially, it's probably going to take just about the same time as well. So it's not going to give us a huge performance in this example for various reasons. But even if we were to celebrate that we got a better performance, let's just say, okay, we did. But notice what just happened. Is the code very much same as the one we had a minute ago? Sequential versus concurrent. What do you think? Yes or no? Those who are saying yes are not listening. Because look at all the things we had to do. We are doing 2 loops now and not 1 loop anymore. So again, is the code the same as it was before? No. It's very different, isn't it? Because you had to first grab all your futures. Then you had to loop through your futures. So the code is fundamentally different. In fact, had I had multiple objects that I have to maintain, this code will very quickly turn into a monster. So what happens normally? You start writing sequential code on projects, and if you're recording, please don't record, please. So if you are writing sequential code, then what's going to happen is when you write the sequential code, the code has a certain structure, obviously. So in this case, the code has some structure, But going from sequential to concurrent entirely changes the code structure, right? This has been our experience in the past, and we suffer through the consequences of it. The more complex the problem is, the more monstrous the code becomes when you turn into concurrency, and that becomes a nightmare to deal with it. So what do we do about it? Well, this has been our past. This has been the past till Java 7. Well, okay, so how does this change when it comes to maybe Java 8? So let's talk a little bit about what Java 8 Stream actually does. Let's try this again. So let's get back to the code we had a minute ago, which really had that one loop in here. So let's go ahead and bring that one, so some square root. And let's just grab that old code and bring it in and see how that's going to be different. Well, here's the code again. I'm just going to run it to make sure it still runs. This is the sequential code after all. And then, of course, what I'm going to do here is go ahead and change it to using streams. Well, notice we can then say import java.util.stream over here. And then in this case, of course, we have sum of squares. So when we have sum of squares, well, I want to use a stream API to do this work. But what does this really do? It takes the square root of all the values and totals this up. Well, okay, that's easy to do with streams, isn't it? So return, and I'm going to say int stream.range, and it's a range closed after all. And then I'm going to go from 1 to the given number. Then I'll perform a map to double, and I will simply call math.square root right here. And then once I find the square root, I'm going to perform the sum operation. So notice what we just did. We converted the code from the imperative style to the functional style in Java 8 using the streams API. Now, obviously, a code is of no use if it's just beautiful. It's got to still give us the result it needs to give. And we'll find that out in just a minute. But would you agree the code is more concise than it was a minute ago? It's fewer moving parts. It's easier to write. Now, is it sequential or parallel right now? Still sequential. We didn't change that part at this point. So let's get rid of that part. So that's a lot more concise. So we got the range of numbers, from the square root of it, totaled it. Great. Let's come back and attack this code now. We want the sum of the square root, so what do we do? Well, exactly the same idea. We'll say int stream.range, in this case again, closed. Start with 1 to max, but this time we will say map to double again in this also. And going from map to double, we're going to call the sample sum of square roots function. And then we will simply call the sum to total this up. And in this case, of course, we got the value that we are interested in using. So we'll say over here double, and of course save it to sum of square roots equal to, and we will simply save it. So we made the change in this case to using the Java 8 streams. Now let's go ahead and run the code and make sure that it's still working. It should give us the same exact result as it did a minute ago. And in this case, of course, it was 1.49 e power 11 is what we got earlier, and it should be about the same. So you can see 1.49 e power 11. Again, don't trust the time too much here, but the point is it gave us that result as we saw here. So the result is the same, sure. But the code is a lot more concise, it's more elegant, this is awesome. But one of the things we just did here is the nice little map reduce problem. So if you notice, we did the mapping right here, and sum is nothing but a reduce function. Sum is more of a specialized reduce function. So all we did here was a map reduce. So by doing this map reduce, we are able to take the collection and map it and then reduce to a single value. So that exactly did what we wanted to do. But I want to really run the code in parallel. Now remember, when we wrote the code using imperative style, and to make it parallel, what did we do? We first brought in the executor service. Then we started creating a collection of futures. Then we started collecting all these future objects into the futures collection. Then we started looping through and then went through the future object to get the result. And of course, that's only the tip of the iceberg. It can explode into more complexity as time goes on. But we are not writing the code using imperative style in this case. What we have done here, of course, is using the stream. So what do? I want to run this in parallel. So I come in here and say parallel right here. And even if I chose to, I can make this one parallel also. So I can just drop in the little parallel as this call right here. That's the only line I added just now. I didn't touch the top part. Now I go back here and run the code. And what is this going to do? It's going to branch off threads and run it. Now notice it gave us exactly the same result, didn't it? But of course it took a lot less time than it did before. Again, if you want to ignore the time, the point is the result is still the same. But here's the question for you. Is the code structure very different from what we had a minute ago? Yes or no? No. The code structure is exactly the same, isn't it? In fact, let's try this a little differently. What you could actually do is you could potentially take these two lines and roll it into a method. Then when you call the method, you can just pass the in stream to it and it will run sequentially. Or you can call exactly the same method but pass the call after parallel and it would run parallel. In fact, the method will be exactly the same, but depending on whether you sent a sequential stream or a parallel stream, the method would behave differently in terms of its execution. So for the very first time, we are beginning to see a code structure that is exactly the same, whether you program it sequential or concurrent. This is not trivial. This is a moment where you take a little piece of kerchief and you weep into it and say, oh my gosh, this is different, right? The tears of joy flow through and you hug everybody near you and say, did you see just, there you go, he's doing that right there. That's exactly how I felt about it when I came across this, right? It's like, are you kidding me? I spent all my youth writing code in concurrency and all the time I wasted. If only I had this as a kid, I would have been a lot different person growing up, right? Maybe I won't have as many gray hair as I do today because I would have been able to write this code. So the beauty is, what does Java 8 parallel streams do? That is the first question we need to ask ourselves. So the very first question we're going to ask here is, so Java 8 streams preserves the code structure. So preserves the code structure for sequential and concurrent execution, right? So that is the very first observation we need to take home. So until this point, until Java 8, we did not have that facility. The code structure was completely different. And what I showed you was, in the earlier case, was only marginally different. But it can turn into a monster completely, and you won't even recognize it. That, oh, this was a sequential code, this is concurrent, that is completely gone. But with Java 8 streams, and again, I want to emphasize, Java 8 stream doesn't solve all your concurrency problems. It fairly nicely solves the problem of dealing with a collection of data and making it parallel. That it does. So the point really is, for the first time, the code structure is exactly the same, whether it is sequential or whether it's concurrent. With me so far? So is that an improvement? Absolutely, right? So the question is, why not just be happy with Java 8 and stay with it? Well, now comes the next challenge. We are dealing with big data. When you deal with big data, what do? You are going to take a large volume of data, in millions and millions and millions of data, and you're going to do number crunching on it. So there are two kinds of operations you can perform in general. One is the computation intensive, and the other is I/O intensive. So what does a computation intensive operation do? It just keeps churning through numbers. You could take your data and throw it into a bunch of equations, and the equation says, gosh, you fed me data, I'm going to go work on it, right? And it runs for God knows how long it needs to run, and then it spits a result back at you. If that's what you're going to do for one piece of data, imagine doing this for millions and millions and millions of data. That's going to keep churning for a very long time. On the other side, you may take a piece of data, throw it into a function, and that function may take the data and say, excuse me, just stay put. I'm going to go make a request to a web server or a web service or go to a database or go to a file, and I'm going to get some information, and once I get the information, I'm ready to do some work. That is an I/O intensive operation. Now here comes the problem. If you give me so we said there are two kinds, right? One is computation intensive, and then of course the other one is I/O intensive. If my job is computation intensive, so if a job is computation intensive, never give more threads than the number of cores, right? This is a rule we need to keep in mind. If your job is computation intensive, never give me more threads than the number of cores. Now, why is that? Imagine I have 4 cores, and imagine you give me 4 threads, and the threads are going to work on computation intensive work. What's going to happen? Those 4 threads latch onto the 4 cores, and they keep running on it, right? No problem. They're busy. The core is there to serve them. Awesome. Now take 8 cores and put them on this 8 threads and put them on these 4 cores. What's going to happen? The first 4 threads go on the cores. They get on it, they run for a little bit, and then the time comes where the context switching has to happen. Do these 4 threads have more work to do still? They do. While they have more work to do, you're saying, oh, excuse me, threads, I have to interrupt, sorry, get off my core, right? And then you're taking these other 4 and you're putting on it. What do these 4 guys do? They're waiting. I still have work to do. You're not giving me the core. And these guys get on it. They run for a little bit and you're saying, get off my core now because I've got to get on it. So here's a scenario. Say that there are 2 treadmills. And imagine there are 4 monks. You know how monks are the politest people in the world, right? So there are 2 monks. The 2 monks get on the treadmill. As soon as they get on the treadmill, they look down and say, oh my gosh, you're waiting for a treadmill, aren't you? And they immediately get down. And the 2 monks who are on the ground says, thank you very much. And they get on the treadmill and they look at, oh my gosh, you're waiting for the treadmill, aren't you? And they get off. And what happens? The treadmill, they keep jumping on and jumping off the treadmill. You know, it pays to be rude in life sometimes, isn't it? No, just kidding. But the point really is that they're not going to work out at all. They're going to be just trashing. And that's exactly what's going to happen. On the other hand, if you have I/O intensive threads, what's going to happen? I take a thread, I give it on the core, it runs a little bit and says, give me a second, I'm going to go get this stuff from the database over there. And the core says, yeah, go on. And what are you going to do? I have nothing to do. You might as well work on another thread now. So as a result, if it's I/O intensive, you can put more threads on a single core, which means in an I/O intensive, you can give more threads than the number of cores. But of course, if I walk away saying you can give more threads, you're going to say, how many? Well, the beauty is almost everything in life is math, isn't it? This turns out to be actually an extremely simple math. So you can say number of threads is equal to, and a very, very, very simple math. And that is the number of cores, so number of cores divided by, and you can say 1 minus the blocking factor. Very, very simple math, as you can see. So how many threads should you give me? The number of threads you should give me is number of cores divided by 1 minus the blocking factor. Well, in a computation-intensive thread, what is my blocking factor? 0. So that means number of cores divided by 1 minus 0, which is equal to number of cores. So for computation-intensive, give me no more than number of cores. If my blocking factor is 50%, what does it mean? I'm going to sleep for 50% of the time because I'm going to be doing I/O. Well, then number of cores divided by 1 minus 0.5, and what does that become? That's 0.5 in the denominator, which means you can give me twice the number of cores, which is very intuitive to see, right? Because if it's sleeping for half the time, your core can work on 2 threads at the same time. You can have as many times as 2 times of the thread. So the point really in this case is, you say that number of threads is less than or equal to. So that's the formula, less than or equal to, where, of course, the blocking factor is 0 less than or equal to the blocking factor less than 1. So if it is 0, what does it mean? It's computation intensive. If it is 1, what does it mean? Deadlocked, right? You don't want to ever touch that 1. So you're close to 1. You still have hope of finishing eventually, but you are waiting for a long time to get the data. So the point really is, this is what you have to do. Now, let's talk about the problem. So I have a very highly computation intensive job at my hand. I've been given about 20 million pieces of data. And for every piece of data, I've got to do number crunching, let's say. And now, I'm going to create a number of threads to run this. So I have this one machine. Whatever number of cores I have doesn't matter. And I'm going to give it as many threads as the number of cores I have. Now, on this one machine, if I give you that 20 million pieces of data, it's going to run at a certain speed. Now, I'm going to tell you, I want more speed. So I'm going to come to you and say, do me a favor, give me 100 times more threads on this box. Will you give it to me or not? No, why not? What will happen if you give me 100 times more thread? It won't crash. Don't scare the heck out of me. It won't crash. What? It'll trash. Okay. What will happen? Put it in terms that we can understand. What's going to be the result? Yes, it will be slower. Your program will be slower than running it sequential. So you put more threads, what happens? It works slower. Just like our projects, right? You're not progressing on your project. Your project manager, who's the most brilliant person on your team, you know this, tells you, I know how to fix this. Boss, tell me, enlighten me. We're going to hire 100 more developers. What happened to your project? That's the last time ever the hope of ever finishing comes through, right? That's the same thing with cores. Just like we are not going to be doing much work when putting more people on the team, the core says, by gosh, you got more threads, I'm going to keep crashing now. And it'll be actually slower than if it was the number of threads. So the moral of the story, if I need more speed for the problem at hand, what do I have to do? So open the box and put more cores into it. This is like, oh, they sell in cereal boxes. Open the lid. A few more cores now. Now kick it on again. Would that work? What should I do? Divide and conquer. Put it across a cluster of machines, isn't it? Why? Because you can have more cores, just not on that machine, right? So we can get more machines. So now you're saying, all right, that's cool now. I want you to now take this code, but I want you to run this parallel. But I want you to run this parallel not on that machine. I want you to run this in parallel across all these machines. Does it make sense? Now, how do you make this? What does Java 8 Stream do? It runs within a single JVM. Will Java 8 Stream run across multiple JVMs? No. It says I'm a single JVM solution. I'm going to be on this machine. That's all I care about. Oh my gosh, now I have to take this and run it across machines. What do I do? Now we start looking for remoting solutions. You have a data here, I got to send it to that machine, I got a data on that machine, I got to bring it here, and now you're trying to find out what library you can use to move the data around. And let's say you find a library to do that, just as an example. And once you start using that library to move the data around, what do you think is going to happen to the code structure? Will it be exactly the same? No, right? It's going to become a monster. So to go from sequential to concurrent, we dealt with a monster. Now we are saying to go from concurrent to distributed, we're going to have another monster. And something tells me that's going to be a much more evil monster than we had before, right? So now you know what Spark does. So what Spark says is the following. This is the way to think about the relationship here. So let's go back here. Java 8 stream preserves the structure of the code from structured to concurrent execution. Now let's talk about this. What does Spark do? Spark preserves the code structure for single versus distributed execution. Isn't that beautiful? So that is the way to think about the problem it solves. So Java 8 says, I don't care whether you are sequential or concurrent, I'm going to preserve your code structure, which is beautiful. But that's a limitation of Java 8. It says, that's it. I'm going to just keep you in this one JVM. Spark says, don't worry. I'm going to preserve this exact code structure for you, but I'm going to let you run across a distributed set of machines. So this preserves the code structure. Why are we so keen on preserving the code structure? When you write the code sequentially, you can debug this easily. You can understand the code, you can reason it, you can work with it. But if I change the code structure entirely when I go concurrent, all the effort you put in testing it, all the effort you put in understanding and making sure it's correct is all gone out through the door. And you're like, okay, let's roll our sleeves and start over again, right? But if the code structure is exactly preserved, the reasoning doesn't change, only the implementation mechanism changed, so you can leverage all of that. Well, that's exactly what you get here. The code structure is exactly the same on a single machine, but I can go across the machines very easily. Does it make sense? So that is exactly the problem we're trying to solve, is to get that capability. So enough of that talking. Let's see how that's going to work. So for that purpose, I'm going to take on a slightly different problem. So right here, what I'm going to do is to take a little file I have with me, and let's go to the file. So the file I want to go here is this file over here. So I have a file, let's see if I have it here, called input file. Well, this input file is a very large file I have. Okay, reasonably large file. How large is it? So I'm going to ask him, tell me the number of lines in this particular file. Well, and it says I have, let's see what that is, 22 million lines, right? So it says I have 22 million lines of code in it, lines in it. Okay, I want to use that file called inputfile.txt. So now what am I going to do? I'm going to start with this file, and I want to know how many occurrences of a particular word is in the file. So the first thing I'm going to do is I'm going to say spark conf, and I'm going to create an object of spark conf is equal to new spark conf. Now, in the case of a spark conf, I'm going to say set app name, and I'll give you this as a file lookup or whatever. It doesn't really matter what I call it. Set main for a minute, and for now I'll say local to. We'll change this very quickly, but this is good enough to start with. Now I created a spark conf. Now, oh, by the way, Spark was created using Scala, but you can use multiple different languages for this. You can use Scala if you want to use. You can use Java if you want to use Java. You can use Python if you want to use Python, and a few other languages. So you can use multiple different languages, and the API has been modified for different language usage. I'm using Java here, but you can use any language you want to use. So I'm just creating a Spark conf. Because I'm using Java, I am going to say over here new Java Spark context and give a Spark conf to it. And I'm going to save this away into Java Spark context. Had I been using Scala implementation, I would have said the different context over here, just a Spark context, which is what they call it in Scala, but in this case it's a Java Spark context. Okay, now 2 is the number of partitions in this case, a hint towards it. But anyways, what is a partition? A partition is number of divide and conquer, you said, right? Just a beautiful word. So that's how many partitions you're going to divide it into, and you're going to run them in that partition. you can have a one JVM with multiple partitions in it. But you can have a cluster of machines so that you have partitions spread across the machines as well. You can go any number of ways. I'm going to just be on one JVM for a minute because I told you that the code structure is exactly the same whether you're on one JVM or across. So as a result, I'm just going to do it on one JVM for now. So I got this. Well then, what do I do to make use of this? So we create a Spark context. That's what we did. I talked about the limitation of the Java 8 solution a few minutes ago, and I talked about what Spark provides. And what Spark provides is this beautiful thing called RDD. So RDD stands for Resilient Distributed Data Set. The easiest way to read this is to read it from right to left. So the very first word on the right is data set. And that's what it exactly is. It's a data set. But it is a distributed data set. Now this is the beauty of it. It's a distributed data set. So what does that mean? If I create a list in Java, what does the list have? Let's say the list has 10 elements. Where do the 10 elements live? It lives right there on the heap of this JVM. So a list is fully contained within the JVM. Well, an RDD, but a stream in Java 8 is not a concrete collection. A stream in Java 8 actually is an abstraction. Likewise, RDD is an abstraction. RDD doesn't exist in the disk as a data, it's an abstraction. So if I create an RDD with, let's say, 100 people, and guess what? If every row of table here is a node, my RDD has 100 people. How many collections do I have? How many RDDs do I have? I have exactly one. But where are the elements of this RDD? We're not all huddled up here in one corner, right? We are distributed across. Every table has few people. That's exactly what RDD is. So I have one collection with me, but the values for the collection literally could be spread across like we have people in this room, right? So we got several tables, several rows here, and several columns here, and that's exactly how this is going to be. But in the case of RDD, that doesn't even exist at this time. That might come in later on when we actually use it. And the reason for that is, just like streams are lazy, RDDs are extremely lazy. Now, why is it important for RDD to be lazy? The reason RDDs have to be lazy is, if I create an RDD on my machine, in my JVM, and if that goes out and creates millions of data in memory, then what are you going to spend the time on? Moving the data across clusters of machine. Your performance will come down because you're spending time shuffling all this data initially. So the RDD is extremely smart. The RDD says, no worries, I'm ready for you. But it does nothing, right? And it simply sends this request across the machines, and every machine now has a reference to this RDD. When you say, go get the data, one particular node on the cluster will get part of the data, while the other one will get another part of the data, so they can all get different parts of the data, and they can work with the part they need to. As a result, it'll be very efficient. So one of the things to keep in mind is that RDD is extremely lazy. It will not bring in data and do anything until it has to really do the work with the data. How do I get an RDD? There are several ways to get an RDD. One way to get an RDD is to take a list. Suppose you have a list in memory, let's say, for example. You can take the list and you can call parallelize on it, and that gives you an RDD. So if you already have a collection, you can call parallelize, and then that creates an RDD. Keep in mind, in Spark, everything is an RDD. So if you don't have an RDD, there's not a whole lot of work you can do. And so the first mission for you when you start Spark is to go get an RDD. Now, of course, I don't have a list in memory. I got a file. Maybe it's a comma-separated file. Well, that's perfectly fine. You can create an RDD from a comma-separated file. Oh, I got a MongoDB with a lot of data. No problem. MongoDB has plugins that can create RDD for you from the MongoDB database. Similarly, other databases as well. So there are implementations for creating RDDs, But in this case, if you recollect, I had a file on disk, not a MongoDB or any other database, or not a list in memory. So what am I going to do? My mission, first mission, is to get an RDD. So I'm going to go here to Java Spark context and call this method called text file. But before I call the method called text file, let's just say text file for a minute, and notice the return type of that. It would be an RDD had I been using Scala. But because we're not in Scala, because we're in Java, they gave us an API that is convenient to use in Java. That's why it's called Java RDD. But don't worry about it. It's just RDD. It is RDD with a little flavor for us to easily use from Java. That's the only difference. So notice the text file returns RDD. That's what it's returning for us. So I'm going to say text file right here. And then the name of the file I'm going to provide is, in this case, input file.txt. Well, good news, I got an RDD. Well, what does this RDD have? It has lines and lines and lines. How many? 22 million lines of text. So what am I going to do now? I'm going to say flat map. So why am I using a flat map? Well, when you have a function that goes from a single value to a single value, you can apply a map on it. And that way you give a collection and apply the map, you get another collection. But on the other hand, if you have a function that takes a single value and gives you a collection of values, well, tough luck, you cannot use a map, because if you use a map, you go from a collection to a collection of collection, which is kind of, hard to deal with. So a flat map says, if you give me a function that takes a value and gives you a collection of value, I'll flatten it out and I'll still give you one collection and not a collection of collections. So that's why we are using a flat map here. So what am I going to do in this case? Well, I'm going to say, given a line of text, I'm going to then say line.split on the space. So in other words, I'm getting the words in the document, right? And once I get the words in the document, unfortunately, flat map requires an iterator to be returned, not just array. So I need to get an iterator out of it. Well, I can get an iterator out of it. So I can say arrays.asList, and I can provide the collection of data right now, and then I can ask it to give me the iterator around it. And now we can say, what do we have at the end of this call? Well, at the end of this call, we have words in the file. Well, if you want to be very technical about it, at the end of this call, we have absolutely nothing. And you know why? Because it is lazy. It says, yeah, I'll do this eventually. So it's lazily going to do the work, right? But it's going to be words. So then I can perform a filter, and I can say, given a word, what do I want to do? Given a word, I'm going to say word.equals, and I'm going to look for the word the. So, okay, then I'll perform a map, and I'll say, given a word, just give me a 1, if you will. Then I perform the reduce operation, and in this case, I can say total, well, let's start with the little 0 value. I can say total, comma, the value count in this case, and all I'm going to do is simply return a total plus count. So this could be the return value that I'm going to return from this particular object, and I can say I want to perform the total plus count value and return it. Well, okay, so what is this going to do? We'll come back and fix this in a second. So this is saying, given the collection of files, get me an RDD, and once you get the RDD, get me all the words from the file. Once you get all the words, for every word, only get me the words that are the, and if you find a word the, give me a 1, and when you give me a 1, perform a total operation to count those values and give me the result. So let's see if that actually works. So I'm going to go ahead and run this now and say, go ahead and execute it. So this is going to be executing this particular call and get us the result. Well, to make my life a little bit easier here, what I've done is I have created for myself a little build.gradle file. And in the build.gradle, all I have here, if you notice, is a little thing called run sample that I'm going to use to run it. I mean, you could run it from the IDE as well, but in this case, I'm going to say Gradle W, and I'm going to run the sample. So in this case, of course, we are asking it to run through the file and get the result, and it runs through that. And let's ignore those things for a few minutes. We'll come back and talk about what those things mean. But this is Spark kicking in and doing its work. And then we can notice the output it produces for us. And right about somewhere here, it should tell us the result. Well, okay, that's a little hard to see, isn't it? So let's do something else. Let's come back here and put a little output. Just for our purpose, it's a little easier to see it. Let's put a little few asterisks here. So that way we can quickly point to where that's appearing in the output. So let's go ahead and try that. So let's go ahead and see what it's going to produce. Let's run this now. And what does it show? It's going to show us the output. Right there is the output running through. And it's going to produce the result of it. That didn't go very well, did it? Okay, so it should give us the result somewhere of the number of words it found. See if I can actually find it. A little too noisy for the log outputs. Otherwise, I'll grab this and search it in just a second. So give me a second to scroll through and find it. So eventually, it will come back and tell us what the number of lines is. All right, I'll do that. I'll just grab this and do a quick search on it so we can actually find it. How about this? So let's go ahead and say, open it up in the editor. And so maybe we can look at it once it comes up in the editor. Okay, so that's all the log value that it's displaying. So, and once it's done, in the editor, hopefully we see the result. That is awesome. So notice, right there it says, what is that? How much is that? 4.6 million occurrences of the word the. Well, how much time did it take to run? Well, okay, to be fair, I'm compiling it and I'm going to run it also. So the overall time is going to be the time it takes to do the whole work. But you can measure the time for whatever it takes. But the point really in this case is, it got us the result. But before we go further, just quickly take a look at this for a second. If you look at the log, we will notice this is a beautiful thing to look at. What does this say? It says, I'm going to be in a partition. I'm going to read the file input file.txt. But what does this say? I'm going to read this offset into the file. So even though that's one big file with 22 million lines of text, this says, I'm not going to read the entire file. I'm going to read from that offset onto that, and that is what this partition is doing. And then if you scroll a little bit up or down, doesn't really matter, you will come across yet another scenario where you're reading a different chunk of the file. So you can see all these RDD parts are being read by different things. So what does this tell us? If I now go across machines, this RDD is going to be spread across, distributed across these machines, but each of the nodes will read different parts of the file, isn't it? So how do I go across to a different machine? Well, let's give it a try. So now that this code is working, what do I want to do in this case? Now that the code is working, I want to actually distribute this. Well, remember, to distribute, you don't want this to turn into a monster, isn't it? So I'm going to just remove this one-liner, and now I have just put it as set app name. And I've not given any other details about where to run and other things. So this is set app name. Now, I'm going to simply run over here. Let's look at the build.gradle for a second. In the build.gradle, I have a little configuration called jar that's going to create the jar file. So all I'm going to do is run Gradle and run jar, and it's going to produce a jar of that particular code. In this case, it's going to produce the jar of that particular file. So let's make sure that I have the things done right here. So it's giving me a compilation error. Let me find out what it is from. So this is going to be removing this part, and I'm going to ask you to just compile the file and give me the jar. So let's try this one more time. So I'm going to say, let's just run this for a second. Just compiling it, and okay, failed. Let's see what the compilation error says. I have a little syntax error. Maybe you can help me to fix it. So what happened over here? Is this an extra parenthesis? So this is going to be, do you see it? Line number. Give me a line number. 19, thank you. Should I remove this one? Okay, thank you. All right. So let's go ahead and try this again. Thank you. So run that and see if it compiles. And yep, build successful. Let's just create a jar. Now, I just bundled it into a jar file. That's all I did. Now, if you look into the build libs directory, I have a Spark example.jar. I just created this as a jar. If you notice really quickly, ls minus lh, you will notice that the build libs, simply that file, is a little tinny mini 3.2K in size, right? It's a little small jar with just the code that we just wrote. Okay, so now what do I want to do? Well, what I'm going to do now is, I'm going to first of all go into where Spark is located on my machine. So I'm going to go to Spark. And Spark, by default, uses Hadoop, but you can use various different things if you're interested in other things. So I go into the sbin directory, and I'm going to do, in this case, a start master.sh. The start master.sh, and there are different ways to start this also. This is just one way. So I'm going to run a start master. So when I run the start master, it simply starts a master server. So a master server is running on my machine. When you want to distribute across Spark, you can do this programmatically if you want to. But what I'm going to do is, I'm going to take my job and say, hello master, here you go. And the master says, thank you. And the master says, I got slaves registered to me, and I'm going to take this problem, create the RDD, and distribute it across to the slaves. The slaves can now run the program, get the results back to the master, and it's going to give it to you. Well, so this brings up to a few things. There are stages and the partitions and the stages and the shuffles. A stage is a sequence of execution. So this is a pipeline that you're going to execute. That's a continuous flow on a given node. But when a node finishes the job, what is it going to do? It's got to take that result from the node and bring it with the result from other nodes together. Imagine for a minute if I'm going to ask everybody to total their age. Well, because we have people on different rows here, these people may total their age, these people may total their age, and so with every row. But then I may take the sum in each row and total that together. So that is the shuffle, because the value is in different nodes, and I got to bring them together. So shuffle process is to bring the data from multiple nodes together, and that may result in redistribution for more work after that as well. So in this case, I created a master. The master is running on port 7071. That's the default. But I'm going to open up right now http://localhost 8080. And when I open that, this is displaying a 7077 rather, and it's displaying the installation of Spark, as you can see right here. And it says that I don't have any slaves connected. I don't have any applications running right now. Okay, we'll come back to this in a few minutes and look at it, so we'll minimize it. The next thing I'm going to do here is, I'm going to do a start a slave. So I'm going to say start, and this is going to be slave. And when I start the slave, I've got to give it a few details. I've got to tell him where the master is located. So the start slaves requires the details about the master. I also, so that way it can connect to it. So in this case, I'm going to say Spark : agility is the name of my machine. 7077 is the port where that is connected. So all I did was I started a slave. That's all I did. Now that I started a slave, if I go back here and refresh, notice now I have a slave worker ID sitting here. And it tells me the slave is alive and it's got 8 cores. I have a little puny 8 cores on my machine, and that's what it tells us right there. So it says that I have a slave running on this machine. Well, again, minimize, we'll come back to it. So now we have started a master, we have started one slave. Of course, in reality, you wouldn't want to have one slave, you would want to have many, many, many different slaves. In reality, you don't want to have 8-core machine either, right? So I'm working with the project right now. We got literally, hundreds and hundreds and hundreds of cores on a machine, and we have many of those machines working for us. So clearly, you would want to have, if you're solving a serious problem, you better have serious infrastructure to do it. So you're going to have a lot of machines and with a lot of cores on it. But in this case, I just created one core. What am I going to do? Now what I'm going to do is, I'm going to go to the bin directory here. And in this case, there is a little thing called Spark submit as a command. So we can use Spark submit to submit a task that we are going to ask it to run. So what am I going to do? I'm going to say over here opt Spark, and I'm going to bring in the, let's go ahead and call in Spark. And this is going to be in the bin directory, and I'll call Spark submit. And once I create the Spark submit, let's bring it in here. And what do I want to say? I want to give it a class that I want to say, class. And the class is going to be agile developer.sample, because that's the name of my class, if you will, that I've created right here. So just saying what the name of the class is. And then I'm going to specify the master, and that's going to be the agility is where this is going to run. That's where the master is located, isn't it? And then you're going to specify the jar file as well after this. So this is going to tell you the location of the jar file, where you're going to run. So all those details you need to specify. I'm actually going to run this without these options and see what it tells us for the options. So let's run this, and it's giving a little error here, which is good. And it tells us here are the options you can specify. Well, the first thing I'm going to specify here, as you would imagine, and you can see there's a lot of different configurations you can specify here as well. But in this case, what I'm going to specify is going to be the class name. Let me actually grab this so that we can see it in a little bit better way. So let's go up here, and I'm just going to grab this output real quick, and then we will take a look at it in a little bit easier format than the big font I'm using right here. So this is simply running the submit to submit a job to the master. And when you submit a job to the master, what is it going to do? It's going to create the RDD in the code, but distribute it across the node. In this case, we have only one slave, but it's going to distribute it across to that. And then, of course, it's going to come back and run it within that. So to look at the options we have in here, I mentioned there's a class option. That's what I wanted to use, this dash class you can see here. There's a jars to say where the jars are located, and then I'm going to specify a master to say where the master is located. That's what we're going to specify. And then it's a Spark and then the location. So let's try this again. So I'm going to run the Spark. So class agile developer.sample, and then the next one is master, and this is going to be Spark : agility 7077, and then jars, and that's going to be build libs sample example.jar. So that's what we are specifying to start it. Let's see what the error says here. Exception in main, missing an application resource. What is it complaining about? It says check arguments. That's kind of weird. Let's make sure I'm in the right place. So I am in the Spark example. Let me try this real quick. Let me try without the jars for a second. Maybe I'm making a configuration error here. Otherwise, I'll pull my example and run it. If it fails, okay, there you go. So now you can see it started. Oh, in the meantime, let's go here and quickly take a look at the output. And now you can see an application is actually running right there. So it says, notice in the beginning, we had this server running here, master. It says that I have one node running here. And then it tells me that I have that node running this application. And it says that application is running, and then of course it says the duration is 5 seconds, it says. If I refresh this, you can see that it's no longer running, but if I come down here to this, it says it finished it, and it took about 7 seconds to execute. That's what it says, right? So that is basically what you saw here, is that it ran on one node. But I want to show you running on multiple clusters. But for that, what do I need? I got to bring in other machines to execute. And when I bring in other machines to execute, of course, I need to have this file available on this. You either can distribute the files across, or you can use HDFS to access the files across and things like that. But of course, I don't have other machines to reach from where I am right now. So I'm going to do something, but I want your input, whether it's a good idea or a bad idea. I'm going to start 5 slaves on this machine. What do you think? Is it a good idea or a bad idea? Why is it a bad idea? Exactly, right? If I could start 5 cores on this machine and run, I could have just run this in Java 8 with more threads, right? So your performance is going to be slower if you put more on this box. You understand that, right? So never run more nodes on a single machine. Having said that, I'm going to run more cores on this machine just for us to see the execution, right? And of course, it'll prove the point that performance is going to suck as well. So here's a little trick. I'm going to go to the start slave over here. Well, not there, over here. So let's go to the sbin directory. And in the let's go here to sbin. So in the sbin directory, I go back to the start slave .sh. And in this, we have one little thing called Spark Worker Instances. So I'm going to just, and again, don't do this, right? Equal to 5, and I'm going to say start slave, and then, of course, I'm going to specify where the master is located. So Spark colon / I'll move this a little bit so we can actually see what I'm typing. And then agility, so agility, and then colon, and this is going to be 7077. So this is starting 5 different slaves, right? So there you go. You have all those 5 different slaves which has been created. Now, you can see that if I had other machines, those will show the same thing here, except the addresses will be different, right? For whatever machines they are connected to, it's going to show you a different location where it's coming from. Whereas here, notice that all these locations are exactly the same, but in reality, it'll be coming from other places. Okay, so now I'm going to go back and run the program again with the same thing we did, submitting it to the master after all. Now what's going to happen? Well, if you notice, the app is running. Did you notice it's telling me I'm using 40 cores? You know that's a lie, right? Poor program thinks, oh my gosh, it's giving me 40 cores. But all the 40 cores are exactly the same 8 cores, right? So you know this is not going to be fun running this. But the good news is it should still produce the right result when it's done. But when it's done, what's going to happen? It's going to tell us how much time it took to run. And notice it took 12 seconds to run. The point we made earlier, right? Putting more threads on a single machine is like putting more people on a software project, right? You're going to come to a grinding halt after a while. That proves the point. But it also proves the point that it did distribute it across and ran it across these nodes, except that you don't want the nodes on the same machine. You'd want the nodes on a different machine. But I've done this where I have many other machines and with a lot more cores than 4 or 8. And the behavior you notice will be no different than what you saw here. It's going to be exactly the same. So that's basically what we did. We distributed it and I ran it across and got the response from it. And so that is basically what we achieved, is by running it on a single node and running it on multiple nodes. But hopefully you can go back and try this on multiple different machines. And I hope that was useful. Thank you.
Thank you, Venkat.